So today we are looking at 505, the zeros in multiplicity, but I am going to skip ahead because this is dealing with some factoring practice that we can look at next time with division. I want to look ahead and actually dig into some of these graphs. So our goal is to analyze an equation of a polynomial in factored form to figure out what the graph is going to look like. And I was just saying, but not on the video, I was just saying that there's two types of x-intercepts. And when you look at the x-intercepts of a polynomial function, sometimes an x-intercept might bounce off the graph, and sometimes it might cut through the graph. So what makes it bounce off and what makes it cut through is the multiplicity of the x-intercepts, or the zeros. And so that's what we're looking at today, is the multiplicity. All right, so when I look at the degree of a function and it's in factored form, I have to think, if I multiplied all of these x's together, what would I get in standard form? So what is x times x squared times x? It would be x to the fourth degree. So the degree would be 4. So that's important to figure out our end behavior later. And then it says, what would be the maximum number of x-intercepts? Whatever the degree is, tells you the maximum number of x-intercepts. It doesn't tell you there has to be 4 x-intercepts. We know that some polynomial functions actually have 0 x-intercepts. So that's why we say there's a maximum of 4, but there might not be 4. And then the maximum number of turning points, this is kind of a new idea, but if I generalize something for you, how many turning points does a linear function have? 0, right? How many turning points does a quadratic function have? How many turning points could a cubic function have? Do you notice a pattern? So this was a linear function, degree of 2 quadratic, degree of 3 cubic. The number of turning points is going to be 1 smaller than the degree. So in our chart here, this is going to be 1 smaller than what our degree was. If our degree is 4, there could be 3 turning points on the graph. So sometimes you might see something that looks like this, 1, 2, 3 turning points. But you also might just see a quadratic looking function that only has 1 turning point. So it doesn't say that it has to have 3 turning points, but that's kind of a rule. And I'm not going to have you memorize all these rules, but I do want you to know how to find the x-intercepts from factored form, because we've done this before. In factored form, what does x have to be to make 0? So from the first factor, 2x, x could be 0. And I'm going to actually put them kind of in a column, because next to it, I'm going to state the multiplicity of each one over here. So x could be 0. What about from this factor, x plus 1? What would x have to be as the x-intercept? -1, just like we did last unit. And then what about 2x minus 3? If I set 2x minus 3 equal to 0, what will I get for x? I would add 3 to the other side, and then do what? Divide by 2. So 3 halves is my final x-intercept. And then each of my x-intercepts has this thing called multiplicity that has an effect on the graph. And this is what we want to talk about and focus on today. All right, what was the power of 2x? That was just a linear factor, right? 2x was to the power of 1. So the multiplicity is 1, and 1 is an odd number. What about x plus 1? What did it have as a multiplicity? See how this was x plus 1 squared right here? The power was 2. So the power of that x-intercept was even. And then this was just 2x minus 3 to the first power, right? So it again had a power of 1, which was odd. So I want to show you something that happens on the graph. Something very interesting happens at this x-intercept because it had even multiplicity. So you can graph it on yours if you want the close-up view, or you could just look at it on mine. But I'm going to go to the y equals menu, and I'm going to type in 2x, and then parentheses, x plus 1 squared, and then parentheses 2x minus 3. So I'll give you a minute if you're trying to type it into the calculator in the y equals menu. You can just watch me do it. All right, so if I'm just going to hit zoom 6 to get my standard viewing window. So we want to see what is happening at those 3 x-intercepts. So at -1, it just bounced off the axis. And then at 0, it cut through, and at 1.5, it cut through. So even multiplicity makes it behave like a parabola bouncing off the graph at that 1 x-intercept. And that's kind of the big thought for today. So the way that you can figure out if it cuts through or bounces off is by the multiplicity of the x-intercept. So anytime you see something being squared or to the 4th power, it's going to bounce off the x-axis. So on our graph, the odd multiplicity cut through, and the even multiplicity bounced off. And that's the rule for multiplicity. That's the only kind of new rule that we need to add to our bucket of polynomial information today. And so if you look up at the top of this page, I just wanted to kind of show you what it meant before I just read this rule to you. But at the top of this page, it says, so the multiplicity of zeros refers to the number of times the factor appears in the polynomial function. And then what effect does it have? We're going to do a roller coaster exploration, I think, next class. Whenever there's odd multiplicities, it'll cut through the x-axis, and whenever it's even multiplicity, it'll bounce off the x-axis. And so our odd multiplicity in this example, what are my 2 x-intercepts? And my even multiplicity, what's my x-intercept? So here's factored form. We're going to do another example up here at the top. So what are the 2 x-intercepts here that I pointed to? X would have to be what or what? 0 or 3. And then what is this x-intercept right here? X would have to be what? -4. So this deals exactly with what you just learned how to do last unit, except now it's already in factored form. So if you struggled with factoring, it'd be great if you could factor. But in this unit, we're going to look at them in factored form, find the x-intercepts, and then state, all right, what's going to happen on this graph? So when I type this function in, I've got x. Where's it going to bounce off the axis? One place. Where's it going to bounce off? Yeah, what 0 is it going to bounce off of? Which one? So why did it bounce off at -4, but it cut through at 0 and it cut through at 3? Odd multiplicity of zeros, even multiplicity of zeros. I think that's kind of cool. Like, oh, look, it does actually look kind of like a parabola bouncing off at that x-intercept, just like a quadratic would have. But now we've got a higher degree, so a lot of other zeros are also happening. So if you want to sketch this graph, I think it's just helpful as a resource. So we have a 0, 1, 2, 3. Actually, we only need to do it once. 1, 2, 3, 4. So plot your 3 x-intercepts. And this graph went like this. It bounced off. I can't really see where it comes down again, but cuts through, cuts through. I know that it's up because the leading coefficient is positive, and this is a 4th degree polynomial. So even though on the graph it was kind of hard to see that, I know that it bounces off and then cuts through. So this is where we want to get to. Identifying the x-intercepts and the end behavior and the multiplicity. So let's see if you can do number 4. So you're going to write underneath what each of the x-intercepts are, and then use the multiplicity to think about if they're going to be even or odd, bounce off. If you want to try to do it with the end behavior, you could. Or if you just want to wait a minute after you write down the x-intercepts, we could do that part together. But at least identify what are your x-intercepts going to be. So let me finish this example. So we're going to plot 0, 1, and -2. These are both -2, right? So 0, +1, and -2 are going to get plotted. So it says, let's state their multiplicity. This first example was x squared, right? So 0, because it's the x squared term, has even multiplicity. It doesn't mean that the number 0 is even. It means that x squared, the 2, is what's even. X minus 1 just had a power of 1 up here. So the 1 was odd because the power was 1. This is actually a power of 2. So I could have written this as x plus 2 squared. So the -2 has a power that's even. So I'm going to bounce off at 0 and -2 and cut through at 1. But to figure out where to start, I need to look at the end behavior. The leading coefficient tells me what? The right side of the graph is going to go up. So from the furthest right 0, I just draw that that has to go up. I know that the right side has to go up. How about the left side? So if I multiply x squared times x times x times x, what would be the total power of this polynomial? X to the 5th. X squared, x to the 5th is opposite. So from here it goes down. All I need to figure out is what's going on in between with my bouncing off and cutting through. So this says at -2, right, it's even. So it's going to bounce off at -2 like that. And at 0, it's also even. So there must be some turning point. It comes back up, bounces off again, right? And then it must cut through at +1. So I'm not sure how big those bumps are, but I know it goes up, down, and then up forever. Does that kind of make sense? We can go through this whole row of information. So here's my example, -4, x minus 5, x plus 2 to the 5th. What's the overall degree of this polynomial? X times x to the 5th would give me a 6th degree polynomial, right? If you multiplied out all your x's, you'd have x to the 6th. Oh, and you want to pay attention for these last two examples? All right, whatever the degree is the maximum number of x-intercepts. And the reason for that, if you think about your friend a linear function, how many times can a linear function cross an x-axis? Once, right? How many times can your friend the quadratic cross the x-axis? Twice. How many times could your friend a cubic function cross the x-axis? 3 times. It doesn't have to though, right? A quadratic might never cross the x-axis. So this is called the maximum number of intercepts. The maximum number of turning points we said was 1 lower than the degree. Because a linear function has 0 turning points, a quadratic function only has 1 turning point, cubic function might have 2 turning points. All right, so then find all x-intercepts. I only have 2 x-intercepts in this problem, right? One is at 5, and one of them would be at -2. And then it wants you to state what the multiplicity of those x-intercepts would be. So what would you say? Even or odd? They're both odd, right? This was to the 1st power over here, and this was to the 5th power. So it's basically the individual degree of the factor tells you the multiplicity. So these are odd, and so it's going to cut through the x-axis. Odd cuts through. Even is a parabola, bounces off. All right, so this last example is the reason why we learned division. So they're telling you that x minus 1 is a factor. So what you're going to do is you're going to divide by x minus 1 to bring it down to a quadratic, then try to factor the quadratic. So I'm going to help you do this one. So we've got x minus 1 is what we're dividing. And I'm starting with x cubed in this top left box. So I'm trying to make x cubed, so I need my quotient to be x squared, right? And then I take the x squared times the -1, and I've got negative x squared down in the bottom. And I'm trying to get to positive 2x squared. So what goes in the next box? If I'm trying to get to 2x squared, then I need 3x squared, right? To get to 2x squared. So I'd put plus 3x next. So what's going to go in my bottom box? Negative 3x. Now I'm trying to get to positive 5x. So what do I need? Oh, wait a second. I'm at -3. I'm getting to 5. So don't I have to add 8x? All right, so my plus 8 is the last term of my quotient, and voila, I get -8 down here, so there's no remainder. And there shouldn't be a remainder if it's a factor. So this function is really x minus 1 times x squared plus 3x, minus 8. Can anyone take that quadratic one step further with the, oh, wait a second. I can't factor that, can I? There's no factors of -8 that are going to add up to the 3x. So we'd have to do quadratic formula on this, which I'm not going to do right now because I think there's no solution to this quadratic. There might be. I'm not doing the quadratic formula. I thought this was going to come out factorable. Surprise! So let's do it based on that one factor alone then. So let's answer the questions. What is the degree of this original function? It's x cubed, right? So what's the maximum number of x-intercepts? And what's the maximum number of turning points? 2. Right now, it's just x equals 1, because I don't know if I want to do out the quadratic formula on that. And x minus 1 would be odd multiplicity, right? So let's just take a look at the graph to wrap it up here. So if I take a look at the graph and just see what happened, x cubed plus 2x squared plus 5x minus 8. Let's just take a look. We know that it's going to cut through at 1. Oh, and actually look, so there was no other solutions, right? It does something funky, but it just cuts through at 1. So if I had done the quadratic formula, there would have been no extra solutions here. My goal is on a quiz to give you a factorable quadratic here. That's like kind of an easy one, like with the diamond, so that you could get the next set of factors from that. But for now, this one was just a cut through. So maybe that's enough to get you started on multiplicity, the even versus the odd. And we will go back and do the front page of this kind of as a warm-up next time, finding the factors using division, because that helps us with our operations.